Hi, I'm Valley from Greenwood Solutions. Today's presentation is on prospective short circuit currents, and at the end of this video you'll understand what they are and how to calculate them from a transformer all the way down to a distribution board. But before we get stuck into it, hit that subscription button. Let's get going. Now in the case of a short circuit, the only limit to the current is the impedance of the circuit and the available short circuit energy, and this usually includes the impedance of the supply source, which in most cases is a substation, transformer, or a group of transformers. Now the energy distributor, the DNSP, will usually advise the fault levels for the particular transformer in question. If the short circuit occurs close to the source of supply, the only limit to the current is source impedance. A fault of zero impedance is often called a bolted fault. The impedance of the transformer is usually stated as a percentage of the primary rated voltage that is necessary to cause full load current in the secondary if load terminals are short-circuited. So we're talking fault current situations, and this is determined basically from the transformer or group of transformers all the way down to the final circuit. We'll be talking from the transformer to the main switchboard that is feeding a distribution board via a sub-mains. And effectively the impedance of the cable and the connections as you go down into the system becomes higher and higher, and therefore the fault current starts to decrease. The fault current calculations right at the transformer are based on certain assumptions. A common transformer impedance is 5%. If 5% of supply voltage produces full load current, then with a secondary short circuit and normal supply voltage of 100%, 20 times the full load current will be present. So full load equals 100% over 5. The increasing current demands of modern installations results in an increase in the capability of the supply source to provide high values of short circuit current. So let's assume a three-phase 400 volt 500 kVA transformer has an impedance of 5%, supplying the 400 volt bus bars on a factory switchboard. The rated full load current is the kVA of the transformer times 1000 divided by, in brackets, square root of 3 times the rated voltage. So we've got 500, which is the kVA of the transformer, times 1000 divided by 1.73 times 400, and this gives you a figure of 722.5 amps as the rated full load current. The available short current is 722.5 times 100 divided by the impedance percentage. So 722.5 times 100 divided by 5 equals 14,450 amps. And this is the available short circuit current. Look, it really is quite detailed stuff. You have to get your head around impedance, you have to get your head around prospective short circuit currents, and you have to get your head around some maths in regards to the calculation as you come from the start, being the transformer, all the way down to that last circuit under analysis. So what does this all mean? So at any point in the circuit, apart from the actual point of supply, current would be less than the value of 14,450 amps due to the impedance of the circuit between the source and the fault. Now, the most severe condition would be a three-phase fault at the supply terminals, and the calculations are usually based on this. A fault between two phases would reduce current to about 87%, so you're looking at 12,570 amps. A phase to neutral fault should not go above 50% of the most severe fault, so in this case you're looking at 7,225 amps. The short circuit to earth on an MEN system is the equivalent of a phase to neutral fault. Now the current is further reduced by impedance of the earthing system between the fault and the neutral link. The 14,450 amps doesn't take into account impedance in the HV supply line and the transformer primary. Their contribution is so small, so the calculated values are always on the safe side. Look, at any point in a circuit, apart from the point of supply, that prospective short circuit current is going to be less, obviously because of the impedance of the components involved. Now, the calculations are always done with a large safety margin in mind, as they should be. So in a lot of cases, the impedance from very small aspects of the installation are not included in the calculations. So again, the transformer's impedance, then you've got the consumer mains, you look at the impedance of the cable there, hitting the MSB, and then you work your way down, or in this case, all the way down to the distribution board. We have a look at AS/NZ 3000 2018 version, which states in clause 2.5.2, devices for protection against both overload and short circuit currents, that protective devices providing protection against both overload and short circuit shall be capable of breaking any overcurrent up to and including the prospective short circuit current at the point where the device is installed, and this is really important. In addition, the device shall comply with the requirements of clauses 2.5.3 and 2.5.4. Circuit breakers are not all the same. The ability to break a fault current or a prospective short circuit current varies depending on the circuit breaker, whether it's an MCB or a molded case circuit breaker. So again, what does this mean? The interrupting capacity must be adequate to enable the interruption of the highest value of the current available at the point of installation of the protection. This is a really important point. And the protection is at the commencement of the circuit. This is usually the main switchboard or at a distribution board. The value of the current is called the PSCC, and it must be interrupted before the conductor temperature reaches its limit. The PSCC must be calculated at every relevant point of the electrical installation, basically where the protective devices are installed. Fault level estimation must commence at the source of supply, really important. So you have to find out the transformer rating in question. The energy distributor will provide information stated as amperes per phase or an MVA figure, million volt amps. If supplied with a million volt amp figure, you have to do a calculation. So let's say you get the figure of 10 MVA from the distributor. The prospective current per phase is 10 times 10 to the power 6, which is a million, divided by, in brackets, the square root of 3 times 400 equals 14,450 amps. Any equipment mounted on the MSB must have full short circuit capacity at that point, but the PSCC and therefore the fault current will be less if the switchboard is fed by the consumer mains. So, protection for sub-circuits or sub-mains that originate at the MSB must comply with these requirements. But the fault level at, for example, a distribution board fed by the sub-mains will be reduced due to the impedance of the sub-mains itself. Let's look at the 500 kVA transformer example, connected through a large consumer mains to an MSB, which feeds a DB through a sub-mains originating at that MSB. We know that the PSCC for the 500k transformer is 14,450 amp, and we know that, we've done the calcs. So the impedance per phase of the supply, Z1, is 230 volt divided by 14,450, and that gives us an impedance of 0.0159 ohms. Assume that the impedance per phase of the consumer mains is 0.0037 ohms, and the impedance per phase of the sub-main, Z3, is 0.026 ohms. So the fault level at the MSB is 230 volts divided by, in brackets, the impedance of Z1, 0.0159 plus the impedance at Z2, 0.0037, and that equals 11,735 amps per phase. Now the fault level at the distribution board is again the same kind of calculation, but we add another impedance. So it's 230 volts divided by 0.0159 ohms plus 0.0037 ohms plus 0.026 ohms. And that gives you a figure of 5,044 amps per phase as the prospective short circuit current. With prospective short circuit currents, it's really important to get the data in regards to the impedance of the transformer under consideration, and then you're looking at the impedance of the consumer mains and the impedance of the sub-mains. So effectively, when calculating what fault currents are at different points of the installation, it's a process of starting from the top, being the transformer or transformers, and working your way all the way down. In this case, we're talking to all the way to the distribution board. So at every step, you're doing the calculations where the protective device is actually installed. Now here's a diagram. So effectively, step one, establish that current, prospective short circuit current at the source. Step two, establish the prospective short circuit current based on the impedance of the consumer mains. Step three, determine the prospective short circuit current at the distribution board, taking into consideration the impedance of the supply, the consumer mains, and the sub-mains. Available PSCC at supply source is determined from information from a distributor or a calculation. 2. The fault level at the MSB is determined by using the cable or bus bar impedance and neglect other sources for a safety margin. 3. Fault level at any other position is reduced again due to the impedance of the sub-mains or the sub-circuit fault level. Conclusion. In the case of a short circuit, the only limit to the current is the impedance of the circuit. The PSCC is determined at the start of the circuit at the protection device. All calculations allow a safety margin. Thanks so much for watching our presentation on prospective short circuit currents. If you have any questions, any inquiries, any answers, please feel free to contact us. And before you go, hit that subscription button. See you later.